All right, so we're going to pick up where we left off last time, talking about these addition reactions here of our aldehydes and ketones. We're going to pick up with these two examples here because we're going to complicate things a little bit. All right, so take a second and give me the product that you would expect based on what we discussed last class for each of these two reactions. All right, so in each reaction here, we have our nucleophile that's reacting with that electrophilic carbonyl carbon, which is such a good electrophile because it's in this polar bond with oxygen, but it's also got this pair of pi electrons that can play the role of a leaving group so that our carbon never is left without a complete octet. Okay. So in this reaction here, I didn't ask you to do the mechanism, but if we want to do the mechanism, our first step is that nucleophilic attack. We create that alkoxide ion. Okay. Is this reaction going to be, I guess I should ask you this first, basic conditions or acidic conditions? Basic conditions. And so typically how this would be carried out would be using a mixture of, for example, sodium cyanide. That's how we would get our cyanide ions, but also HCN. And this is just a clever way to do this because then when you deprotonate that HCN, what you're left with is a new nucleophile ion that can turn around and kind of continue to propagate this reaction. All right, so our product of this reaction here is going to be that carbonyl group gets converted into an alcohol group. And we have our nucleophile attached. I'm just going to move this to the page. Boom. Right? Remember that this nucleophile has its own carbon. So you have added one extra carbon to your chain. That's a really common mistake that people make is they stick a nitrogen on there. They forget that carbon is there as well. Okay, so terminology-wise, I didn't make the rules here, but the ion is called the cyanide ion. Really not terribly good for you, cyanide, all right? The functional group, though, as soon as it's attached to an organic molecule, we call this a nitrile, right? That's when it's a functional group in an organic molecule. You'll hear them referred to as cyano groups, but that's a little kind of borrowing from inorganic chemistry. The organic chemists will call these nitriles, all right? So I don't really know why our book decides to introduce these reactions at this point, but we're going to take a second and introduce two reactions of nitriles here. So after we do this step where we add that nitrile group onto our molecule, there's two ways that we can go from here, two more sort of synthetic pathways. Okay. First, we can, let me just reorganize. Okay. So if we took this thing and we added in our LiAlH4, our lithium aluminum hydride. What do we know about this lithium aluminum hydride? It's a reducing agent. And so we saw it reducing these carbonyl groups to alcohol groups. It can also reduce these nitrile groups. All right, again, just adding a bunch of new hydrogens onto this molecule. All right, and so a fully reduced nitrile group would be converted into an amine. We still got that next door neighbor alcohol because we started with this carbonyl compound. All right, but we can reduce a nitrile group to an amine using our normal reducing methods. Lithium aluminum hydride followed up by some sort of proton source, some weak acid. Okay. The other thing you can do is you can oxidize this nitrile group. Actually, we'll chop off that nitrogen and leave you with a carboxylic acid. All right, so these nitrile groups are fairly reactive. So the first two reactions that we're going to learn about them, and we'll kind of pick up on nitrile groups in a later chapter again. These are kind of randomly thrown in here. All right, but with our reducing agent, we can reduce that nitrile group to an amine, and we can oxidize that nitrile group, really that nitrile carbon, to a carboxylic acid using just acid and heat. Okay, so again, we learned about this first step here last class, just taking a nitrile nucleophile and reacting it with that electrophilic carbonyl carbon. And now we know two things that we can do with that product. We can add in our reducing agent to create an amine, or we can use acid and heat to create a carboxylic acid. All right, so now this one. We have this neutral alcohol that we're reacting with our aldehyde or ketone. This would be a reaction that would take place under what conditions? This would be acidic conditions here. Okay, and so we're going to sort of build off this. It turns out that this isn't the whole story. So this is alcohols and ketones / aldehydes under acidic conditions. And this is specific to acidic conditions here. Okay, we're going to do this the long way, show the full mechanism. The first step here, because we're under acidic conditions, is going to need to be a protonation step. So we're going to add in that proton donor for acidic conditions, the hydronium ion. All right, alcohols, not really great nucleophiles, but when we protonate that carbonyl group, all of a sudden we've created this really fantastic electrophile. So even though our nucleophile is kind of weak, our electrophile is a really good electrophile, and so that neutral alcohol can attack that electrophilic carbonyl carbon. Okay, at this point we're not quite done because we use that neutral nucleophile, so we're going to have to go through one more deprotonation step. And what do we use as our base under acidic conditions, our proton acceptor under acidic conditions? Just water, yep. Right, we can't use that strong base, hydroxide. That wouldn't survive under acidic conditions. Okay, cool. So this creates what, now we have this alcohol group on here. All right, I guess it was formerly an alcohol. Now it's an ether group. Okay. This is what's called this product that we just created here is what's called a hemiacetal. But it turns out that that is not the end of the story here. This thing is going to continue to react with alcohol molecules in this solution until it creates what's called an acetal, where we have two of what was formerly our alcohols joined onto that carbonyl carbon, or what was formerly a carbonyl carbon. Okay, this reaction is like kind of gets an outsized shout out in organic chemistry. It's not like it's the most important reaction to an organic chemist, but it's like a ridiculously essential reaction in biochemistry. Every sugar that's ever packaged in your body undergoes these acetal type reactions here. So it gets like kind of a big shout out in this course when really it's like super important in the biochemistry world here, all right? But if we're gonna continue, we need to get rid of this OH group and replace it with another alcohol group, okay? So first of all, it's gonna be really hard to kick off as is because hydroxide's a terrible leaving group. So what strategy do we have for getting rid of these hydroxyl groups? That's gonna work especially well given the conditions of this reaction. Under acidic conditions, how are we gonna kick off this OH group? We're going to protonate it. Yep. So we're going to make it into a better leaving group by protonating it. So we'll have another hydronium molecule coming along, donating a proton to that hydroxyl group. And that just serves that purpose of turning it into a really good leaving group. All right, but exactly what it is that kicks that alcohol group off is probably one of the most surprising steps in this mechanism here. It isn't another alcohol coming and attacking or something like that. It's actually this pair of electrons reforming that carbon-oxygen pi bond that's going to kick off this water molecule. Okay, so everybody take a second, following my electron pushing arrows here. Draw me my intermediate for the next step in this reaction. right? That oxygen donates that pair of electrons back down to that carbon. So now it has this partial positive charge. We've reformed that pi bond. And we have created now another just really good electrophile. So now another alcohol molecule is going to come along. All right, so see if you can't finish off this reaction mechanism, getting us to our full acetyl product here. All right, so the next step would just be that nucleophilic attack of that weak nucleophile, that alcohol. All right, that gets us almost all the way there. We just have one last deprotonation step. And again, since we're under acidic conditions, we're going to use an alcohol water to deprotonate. We could use an alcohol. Okay, and that gets us to our full acetyl here. Okay, so if you have an aldehyde or ketone under acidic conditions in the presence of an alcohol, you're going to get what we expect, that first round of reaction, forming what we call a hemiacetal. But then it's going to keep on going. You're going to have one more addition of an alcohol molecule, forming what's called an acetyl. Okay, and so like I said, this is a reaction that plays an outsized role because of its role in biochemistry. All right, it turns out that sugars, 2, 3, 4, 5, 6, are really just aldehydes or ketones that have a whole bunch of alcohol groups sticking off of them. Okay, they're usually either 5 or 6 carbons long. And really the difference between all those different sugars that you read about is the stereochemistry of these alcohol groups. So they pointed into the board, out of the board, right? You got a whole bunch of stereo centers here. And that's really just what the difference is between all the sugars, is which direction those alcohol groups are pointing. Our body really likes a particular subset of sugars that it uses for energy. And because of this here, because we have both an alcohol group and this aldehyde or ketone group, what you get are these reactions forming these hemiacetal rings. One, two, three, 4. Oh, I messed up my number of carbons. My bad. Okay, and so you'll see sugars represented as these closed rings that have these OH groups coming off of them in whatever orientation. Okay, but that ring closure reaction is that hemiacetal formation. And then how sugars are linked up are these OH groups are attached to one another, creating these full acetyl compounds we call starches, and that's how sugars are packaged in a cell. All right, in organic chemistry, the more interesting, more common use of this type of reaction is actually as a protecting group. All right, so this acetyl formation is unique to aldehydes and ketones. Right? Not the other carbonyl containing functional groups. So carboxylic acids, esters, amides, none of these will form these same acetyls. Okay, so let's take a molecule that contains a mix of two different functional groups. Okay, we have one ketone and one ester. All right, we talked about how lithium aluminum hydride is considered a strong reducing agent. Right, so what would everybody take a second and give me my product of this strong reducing agent on these two functional groups? All right, so this will not only reduce my ketone carbonyl group to an alcohol, it will also reduce my ester, fully reduce my ester to an alcohol as well. All right, what we could do instead, if we wanted to protect our ketone group here, is to create an acetyl using a very clever alcohol here, a diol. All right, this will very favorably create this acetyl because that second alcohol group is in the molecule. And so we create this acetyl here where both of those oxygens are attached to that same molecule. So we got these two carbons in between. Okay, so here's my acetyl group right here. It's now I've got my alcohol group in the same molecule, so they're both attached. My acetyl protecting group. I guess I gotta finish drawing the rest of the molecule. And this ester carbonyl will not form that acetyl group. Again, the acetyl formation is unique to aldehydes and ketones. So now, if I treated this with the lithium aluminum hydride, I've protected that ketone group, so the only group that's going to be reduced is that ester group. Okay. But the feature of any good protecting group that's really important is you need to be able to get rid of it. At the end, you don't want it anymore. All right? And so we can reverse that reaction, that acetyl formation reaction, by just using a large excess of acid and water. That'll help push the reaction back towards just the ketone, or effectively remove that protecting group and replace it with our original functional group. Okay, so in this way we can selectively reduce only one of those two carbonyl groups. All right, so then the last weird one we got to deal with here, we kind of made a point that we were going to omit this specific type of nucleophile until later, and this is the reaction of nitrogen nucleophiles with ketones or aldehydes. All right, so the first weird thing about these particular reactions is they are going to take place under what we're going to call neutral conditions. All right, and I'm kind of lying a little bit. Truthfully, these reactions take place under slightly acidic conditions, but like pH around 5. Nothing too crazy. All right, and the reason why we're going to kind of put it into a different bin in our mind is because of what we're allowed to see under neutral conditions. We can have positive charges, negative charges, or neutral intermediates. We're going to see all the above. All right, so let's just go ahead and dive in here because everything goes great for a while and then shit goes crazy here. All right, so if we're going to use a primary amine, we're going to take our carbonyl group, our aldehyde or ketone rather. Right, by primary amine, to be clear, I mean that we have an alkyl group, but there are necessarily two hydrogens on that nitrogen. All right, so let's just take a specific example here. We'll do a relatively small ethylamine here. Okay. Note that you can't do these reactions under too terribly acidic conditions because then you would create that protonated amine, which doesn't have any lone pairs to play the role of a nucleophile, right? So we can't have this be under crazy acidic conditions or we won't have any nucleophile. All right, so we're under very barely acidic conditions, and the first step is we're going to see kind of violates these basic and acidic condition rules here. Everybody take a second and draw me my product of this very first step here. Thank you. All right, so we get that tetrahedral intermediate, which is what we've come to expect from nucleophiles attacking that electrophilic carbonyl carbon. But here's where we see these kind of bizarre feature of our neutral conditions here. Not only do we have a negatively charged alkoxide ion, but we also have this positively charged nitrogen, all in the same intermediate here. Right? So again, we're going to say that this is allowed because we're under neutral conditions. All right, so at this point here, we're going to do kind of what we would normally expect. We need to protonate this oxygen so that it's neutral, and we need to deprotonate this nitrogen so that it's neutral. Okay? Under neutral conditions here, because we are slightly acidic, our proton donor, or our acid, is going to be hydronium, and our proton acceptor is going to be water. And so we could do this in two steps here, where we protonate the oxygen using hydronium and then deprotonate the nitrogen using water. Or we can do it the lazy man's way, which is to say this oxygen is going to grab that nitrogen, that hydrogen rather. Boom. All right, an internal proton transfer here. Okay? So if we stopped here, this would be kind of what you would expect. Based on what we learned about all the other nucleophiles and how they react here, we have our nitrogen attached to what used to be our carbonyl carbon, and our carbonyl oxygen has become an alcohol group. This is what's called a well, now I'm second guessing myself. Carbanolamine, something like that. Got an alcohol group and an amine group all in the same molecule. But it turns out that this thing right here, for almost, we're going to say all the time, is unstable. This thing is not able to be isolated. This thing is going to continue to react, and in fact, it's going to dehydrate. AKA, we're going to lose that alcohol group from this molecule. So this, you will get to this point in your reaction, but then it just keeps on going, and you have this alcohol group that gets kicked off here. All right, and so what we're going to see is something fairly similar to what we saw in our acetyl formation reaction. First of all, how are we going to get rid of this hydroxyl group? Protonate it, all right? So that's why we have to have slightly acidic conditions here, because of this step right here. We have to be able to protonate that oxygen. And so absolutely, we're going to Use our proton donor, turn it into a good leaving group here. Okay, so now the next step here, we're going to kick off this leaving group. But what is it that's actually going to be kicking off that leaving group? All right, if we look back to our acetyl reaction mechanism here, how did we kick off that leaving group? It wasn't another nucleophile coming and attacking. That's not how we kicked off. It was this lone pair of electrons coming down to form a new pi bond. And so that's exactly what we're going to see here as well. What actually kicks off that leaving group is this lone pair of electrons on nitrogen coming back down, now forming a carbon-nitrogen double bond. All right, everybody take a second and draw me the product of this step here. Let's make sure we can follow our electron pushing arrows. So now we have this carbon-nitrogen double bond. All right, and the last step in this mechanism is just to simply deprotonate this wacky looking thing here. All right. When we're looking at a molecule like this, like acetone, that carbon-oxygen double bond looks super normal to us. We've seen them over and over and over again in 1,000 different contexts. They're in a bunch of different functional groups. These carbon-nitrogen double bonds are far less familiar looking to us. All right, but nonetheless, this is the product of this reaction here, what's called an imine, I-M-I-N-E. And it's sort of analogous to the ketone that you started with, but now you've swapped out your oxygen for that nitrogen. But nitrogen, because it can have 3 bonds, now it also has this however many carbon tail on the end as well. All right, so our aldehydes and ketones, we kind of saved nitrogens here. So let's just make a note. Our primary amines. This RNH2, they will form what's called an imine, where now that nitrogen is double bonded to your formerly carbonyl carbon, and it's got that R group sticking off of it. All right, and this reaction mechanism proceeds fairly normal for the first few steps. We have our nucleophile attacking. We form our molecule, our intermediate here, with an alcohol group and our nucleophile attached to the same carbon. But it doesn't stop there. It's going to continue to react and specifically dehydrate to lose that alcohol group. and we get this carbon-nitrogen double bond. All right, so then what if we have a secondary amine? This now is a nitrogen with 2 R groups and only 1 hydrogen. All right, I want you to try to complete these first 3 steps. We'll use dimethylamine here. A nitrogen with 2 methyl groups sticking off of it. Right, so we get that. What's unique to our neutral condition intermediate that has both a negative charge on the oxygen and a positive charge on the nitrogen. We need to protonate the oxygen but deprotonate the nitrogen. So we can do that all in one shot by doing this internal proton transfer. And that creates what we would expect our product to be, with that nucleophile attached to what was formerly our carbonyl carbon and our alcohol group, our carbonylamine. All right, but again, this is going to go through another dehydration step here. So we're going to get rid of that hydroxyl group by first protonating it, turning it into a good leaving group. All right, but what is it that's going to actually kick that water off? That lone pair on that nitrogen. And so up until now, everything has been exactly identical to our reaction mechanism. for our primary amine until we get to this step right here. All right, again, we have our nitrogen double bonded to our carbon. But if we look at our last step in our previous reaction mechanism, there was a hydrogen that we could just snag off, creating a neutral nitrogen, and that led to our imine. When we use a secondary amine, there's no nitrogen there. Those are both methyl groups. So I can't just remove one and have that be the end here, okay? So what ends up happening instead is another proton transfer, but this time it's going to come from the neighboring carbon. So we have our base, water, accepting a proton, but it's not going to be the nitrogen's proton. Nitrogen doesn't have a proton. It's going to be from a neighboring carbon. That pair of electrons is going to come down and form a double bond while the nitrogen accepts that lone pair. All right, so at the end here we have our nitrogen having replaced our oxygen in our carbonyl group. But now the double bond has moved here to be a carbon-carbon double bond. And this is what we call an enamine. Ene for the alkene, the carbon-carbon double bond, and amine for the amine group, an enamine. Yeah, I don't know who makes this up. All right, so for nitrogen nucleophiles, we have kind of these special reactions to consider here, a little bit different than what we expect. It starts off exactly as we expect, and then things go kind of haywire. So for a primary amine, we get what's called an imine with an I. For a secondary amine, we get those enamines. All right, so then just for the sake of practice here, you don't have to do the full mechanism, but everybody just take a second and give me the products of these reactions. All right, so ammonia is technically its own thing. It's not technically a primary amine, but point being it's got plenty of hydrogens that can be donated. So this will form that enamine, that carbon-nitrogen double bond. This diethylamine, this is going to be a secondary amine. So again, we'll have the nitrogen replacing the oxygen, but not as a double bond because it doesn't have enough hydrogens to be removed. So it's just going to be a single bond, which means that hydrogen had to be removed from this neighboring carbon. All right, so in the first example, we get our imine product. In the second example, we get our enamine product. All right, and then there's one special amine here that we can use. Okay, this thing is what's called hydrazine. Like two primary amines bound to one another. Not really. It's a nitrogen-nitrogen single bond where there's two hydrogens on each nitrogen. All right, so considering this is a primary amine, you're going to treat it as a primary amine. Give me my product here of when we treat a ketone or aldehyde with hydrazine. Okay, so we get our imine product here where we have that carbon-nitrogen double bond. All right, but this compound's a little special because we use that hydrazine. It turns out that if you follow this up with some sort of strong base, like potassium hydroxide, it effectively chops off that nitrogen and replaces it with hydrogens. So this would be a way to remove a carbonyl group altogether. All right, and so we drew it in two steps here, but really when you're going to be using this special hydrazine, you use it as part of this synthesis. Right, so step one would be that H2, H2. Step two, following it up with that base. And again, by doing so, you have cleaved that carbonyl group. This is what's called a Wolff-Kishner reaction. All right, and again, this is a method to remove a carbonyl group. All right, so then the last class of reactions that we're going to talk about for this chapter are what are called Wittig reactions. All right, and they're pretty straightforward. All right, if we let me use a slightly more complicated starting product here. Okay, so we're going to take our aldehyde and ketone and we're going to react it with, I feel like I'm going to F up the spelling here, an ylide. It's something like that. Maybe there's two L's. I don't know. All right. This is phosphorus triphenyl. So if we're going to draw this out here, it's a phosphorus with 3 benzene rings sticking off of it. Okay, and that phosphorus, in addition to those 3 big old benzene rings, is double bonded to another carbon. All right, and that chain length can be any sort of size, but importantly, it has to have at least 1 hydrogen on it. And this big group right here, you'll never see it actually drawn out. This big group would be summarized as PPH3, right? 3 phenyl groups or benzene rings on that phosphorus. Okay, and what we're going to do here when we react this with our aldehyde or ketone, that carbon-oxygen double bond is now replaced with a carbon-carbon double bond from our ylide. All right, so we're going to chop our carbonyl group at the double bond. We're going to chop our ylide at the double bond, and we're going to connect those two to one another. That's what these reactions are doing here. Okay, so then let's just do example. We'll use an actual one here. right, so this is another method of creating a carbon-carbon bond, but specifically, and the only one we know how to do this with, that creates a carbon-carbon double bond. Right, so I'm going to connect my 1, 2, 3 carbons from my ylide to my what was formerly ketone. All right, so we learned how to create carbon-carbon bonds. We know how to do like dehydration reactions to, we know how to create carbon-carbon bonds. We know how to do like dehydration reactions that will create alkenes, but this is a way to create a new carbon-carbon bond and a double bond all in one shot, okay? The one restriction is, again, there has to be a hydrogen on that carbon for your ylide. It can't be just some big gigantic group. All right, so then let's just sort of try to practice some of these reactions and compare here. Let's take our cyclohexanone. All right, we're first going to react it with a methyl Grignard. All right, and then we're going to do a dehydration using that concentrated sulfuric acid and heat. And we're going to compare that to what if we just did a Wittig reaction. All right, so that Grignard reaction is another method that we had for creating carbon-carbon bonds. So that'll put a methyl group onto that carbonyl carbon. All right, but I don't lose my carbonyl oxygen, it just becomes an alcohol group. So then if I take this here and I do this dehydration reaction, concentrated sulfuric acid and heat, we will get our alkene product. But our major product is going to be the more substituted alkene. Right? You always get a mixture, but your major product is going to be the one that's the most stable. So we would get our minor product as this secondary, our di-substituted alkene, and our major product is that tri-substituted alkene. In contrast, if we instead just did this Wittig reaction here, we would be replacing that oxygen with what's on the back half of that Wittig, just that carbon. And so this would be a way of getting all 100% of your product as what would have been your minor product using the other method. Cool. All right, let's just practice some of these other reactions that we learned about here. If we take a ketone, I want you to tell me how we could make the following products. All right, so this thing here, what am I looking at as my product? It had a very funny name. This is the enamine. the ene, the double bond, located right next to the amine, the nitrogen group here. And so this is what we get when we take an aldehyde or ketone and mix it with a secondary amine. In this case, our secondary amine is just this cyclic amine. Right, so both groups are attached. Boom. Down here, this is not an enamine or an imine. This is just an amine group located 2 carbons away from an alcohol group, okay? And to be clear, this is signature of these first types of reactions that we covered at the very beginning. Let's just go back and make a note. If we start with these nitriles here, because when you create your nitrile, you've added that carbon in there. You're always going to get the same pattern with these 2 functional groups where you're, with these reactions where your 2 new functional groups are located exactly 2 carbons apart from one another, right? So if I see an amine group 2 carbons away from an alcohol group, I'm thinking this path here, right? So I'm going to first add in that cyanide, just do that nucleophilic addition reaction. If we were being good, NaCN and HCN. If you just said CN minus, I'm okay with that. All right, but again, we like to use these mixtures here. That'd be step 1, and then in step 2, I got to do that lithium aluminum hydride, followed by that acid step. Okay, so we learned these nitrile reactions that'll create these new functional groups that are 1, 2 carbons apart. We saw this same pattern with what other type of reaction, where you always get these 2 functional groups 2 carbons apart? From last unit, 2 carbons apart, nucleophile, and what functional group? A cyclic ether that is so special it gets its own class of reaction, its own class of functional group. Cyclic ether, it's a triangle. Epoxides, awesome. Epoxides are also, you get these alcohol group located 2 carbons away. And in fact, if we really wanted to, we could have done that same sort of idea, first converting this into an alkene, so that then we could turn around and make a epoxide. Which we could then treat with a nitrogen nucleophile and get the exact same product. This would be like the money is no option path here. It'd be far more expensive to try to do it this way, but you could do it, right? This reaction scheme would also produce the same product. Okay, so again, anytime we see these 2 functional groups, 2 carbons apart, that kind of limits in our mind what the possible reactions were to create that. Cool. All right, we're actually going to continue to talk about aldehydes and ketones, but it's going to be moving on. We're not going to be talking about this electrophilic carbonyl carbon anymore, and we'll introduce that next class.